Hey guys, just want to get together with you today and explain a little bit about strong and weak acids and work some sample problems from the homework. Hope you all are doing well. I miss you guys so much, and feel free to send me a message. Remember, it's Teacher Appreciation Week. Yay, because I so appreciate you guys too. Okay, you should have watched the video which told you the difference between a strong and a weak acid. Strong acids are our friends because they will completely dissociate in water. So that means they'll totally break up and make hydrogen ions and the anion or of whatever else makes up the acid. So that's kind of a big deal. And it makes problems with them super easy to solve. So I'll show you that in a minute. Okay, weak acid problems. On your worksheet, it has this: write the equilibrium equation, write the equilibrium expression, make a table of the concentrations, and substitute the concentrations. You're like, what on earth is that talking about? So I'm going to kind of walk you through that. Again, reminding you that the pH is the negative log of the hydrogen ion concentration, or in this case, this is the hydronium ion. It means the same thing. So if you take a look at your homework problems for today, you have some weak acids and you have some strong acids. What I would do first is I would go and find all the strong acids. So number 1 is a strong acid. Let's see, nitrous acid is not. Strong acid, number 4. Let's see, acetic acid, weak acid, strong acid, number 8. Formic acid and niacin. Okay, well, 3 of them are strong acids. And let's look at, we'll look at number 1. Okay, the pH of a 0.075 molar solution of HI. So let's get a new slide. So 0.075 molar solution of HI. What's going to happen? HI is a strong acid. And so when HI dissociates, it will dissociate into hydrogen ions and into iodide ions. And when it does that, the hydrogen ion concentration will be 0.075 molar. So for strong acids, we just take the negative log of the molarity. So we can do negative log of 0.075, put that in our calculator, and get 2.22. So the pH in this case is 2.22. So if we go back for any of your strong acids, that would be number 4 and number 8, you will do exactly the same thing. You will take the negative log of that molarity. Now, then we have our weak acids, and we have this pesky little thing over here called a Ka. Okay, this is hydrocyanic acid. So if I can remember these numbers, I might have to go back and forth. Okay, well, so we have hydrocyanic acid. All right, we have a molarity. What's our molarity? 0.02 molar, 0.020 molar solution. And the Ka of this is 4.9 times 10 to the minus 10. One thing, kind of a brief introduction with this Ka, this is what's called the equilibrium acid equilibrium expression. Hydrocyanic acid is going to partially dissociate, and that's why we have this double arrow, into hydrogen ions and Cn minus ions. But all of this will not dissociate. And so the equilibrium expression, a Ka, is going to equal the products, which are H plus and Cn minus, divided by the reactants, HCN. And so to solve this kind of a problem, we're going to take our Ka. We know the Ka, that is 4.9 times 10 to the minus 10. We do not know how much of that acid of that 0.02 will dissociate, and so we're going to make that value x. So this will be x, and the Cn minus will also be x. So we're going to say that that is equal to x squared divided by our starting 0.02 molar hydrocyanic acid solution. And the reason that we don't have to subtract x out of this, because what's going to happen is part of this hydrocyanic acid will dissociate. How much? We don't know. X amount. And when X amount dissociates, that's how much hydrogen ions will make, and that's how much cyanide ions will make. My 0.02 will decrease by X, but this number is so small that effectively most of the hydrocyanic acid is going to stay hydrocyanic acid. So now we simply solve for X, which will be our hydrogen ion concentration. So I will take my 4.9, do this in your calculator while I do, second E minus 10 times 0.02, and I get 9.8 times 10 to the minus 12, and then I'm going to take the square root of that. So let me find my second square root, 9.8, second E minus 12. And I get that X is equal to 3.13 times 10 to the minus 6. And X is equal to the hydrogen ion concentration. And so the pH is going to be the negative log of the hydrogen ion concentration, 3.13, second E minus 6. And the pH in this case will be 5.5. You are going to do all of the weak acid problems the exact same way. So if we go back to, we just did number 2, okay? Number 3, you will make the Ka 4.5 times 10 to the minus 4 equal to x squared over 2. Solve for x, take the negative log of that, that will be the pH. In problem number 5, fluoride ions in hydrofluoric acid. Here's my Ka, 6.8 times 10 to the minus 4. Make that equal to x squared over 0.62. Solve for x. That will be your hydrogen ion concentration. Take the negative log of it for your pH. Number 6, acetic acid. Ka 1.8 times 10 to the minus 5 equals x squared over 0.75. X is your hydrogen ion concentration. Take the negative log of it. That will be your pH. Number 7, carbonic acid. 4.3 times 10 to the minus 7 equals x squared over 0.25. Solve for x. That will be your hydrogen ion concentration. That will be your pH. Now, 9 and 10, we get to work backwards. We are given the pH, and we can calculate the Ka. So remember, weak acids, in this case, Ka will equal the hydrogen ion concentration, the COOH minus concentration, over HCOOH. If you know the pH, you can do the inverse log of the negative of the pH. That's going to give you these two concentrations here. Then you can solve for the Ka that way. So I want you to try 9 and 10. And as always, feel free to message me if you have any questions, okay? Super proud of you guys. Let's finish this week strong, and let me know what's going on.